Okay, welcome back everyone. So we're going to move on now. We're going to start by looking at what we've done before in first principles, and then we're going to move to sort of a nicer way to deal with some of the questions that we've seen in the past. Basically, what's going to happen is you'll probably think initially, why didn't we do this all along? And of course, the reason is what we're going to see today will only work for certain questions that fit a nice little pattern. Basically polynomials, but not exclusively. So reviewing, just if we had to find the slope of these two expressions, what I've done, and I didn't write it down, but I'm using the first principles formula without worrying about a specific point. Okay, so I'm not looking for the slope of f at x when x is 3 or when x is negative 2, just kind of working with the expression in general here. And so as we move down, this is f at x plus h, plugging in the x plus h where the x used to be, minus f at x. Instead of using a plus h, I'm just using x again because I'm not going to put a specific number in. And then the limit kind of continues. I've multiplied numerator and denominator by x here, excuse me, and numerator and denominator by x plus h, and then simplified a little bit. So if you don't see what I did here, just write this line down and work it out. It might take you a couple lines in some cases, but this is the correct answer. And then basically as we get down to here, we're looking at dividing the h's out, subbing in your 0, and we end up with -1 on top and x times x, or x squared on the bottom, in the numerator and denominator, sorry. I've been criticized by other teachers for not using numerator denominator and saying top and bottom, but my assumption is you know what numerator and denominator are. So same thing here. Now this is f at x plus h minus f at x on top, again in the numerator. And so as we would have done if this were a 2 or any other number, sorry, if the x were a 2 or any other number, we multiply by the conjugate, the exact same terms here and here, with a subtraction in one case and an addition in the other case. And as we follow it down, the reason we do this is we end up with the first term squared. So we have x plus h minus the second term squared, which is just the x. Again, the x's subtract out as they always have. We have to end up with just terms with h in the numerator. And then my h's divide out. I sub the 0 in for this h, and I have 1 left on top, and I have a root x plus root x, or 2 root x's on the denominator. Okay, so we'll come back to that momentarily. Just a little bit of talk here. So new term we're going to be using, derivative. It's not really section 4.1. That's just the chapter it was in a textbook I've used in the past. So this is more like 1.6 now for us. It's a derivative, excuse me. And we haven't necessarily focused on it, but everything we've done so far is we've been finding slope. Slope, if you remember way back to grade 9, is rate of change. It's the amount that we increase as we go across on a graph. So as in distance versus time, for example, it's the amount that the distance increases over a certain amount of time. So rate of change is just kind of always understood to be the same as slope. Now again, because we're trying to find tangents, we're trying to find slope at a very specific point, we're trying to find instantaneous rate of change as we get into word problems and so on. And we don't do that a lot until a little bit later on, but just sort of understand that you've seen before that rate of change is the exact same thing as slope. It still is. The term derivative now is the calculus term for slope, for rate of change, again, for the limit of, and first principles as h approaches 0. All of these things mean the exact same thing. Just a quick comment here, and I more just had it in because I already had it. Derivative of f at x at some value only exists if that limit exists. Okay, and not really that important, but just to understand that if we had graph like this, and I ask you for the derivative at that point, as long as the limit's there, we're fine. But if we have this kind of a thing where, as we saw recently, the limit does not exist, you can't find the derivative at that point because, again, you're trying to find a tangent to touch that specific point, and of course there isn't one. There's no tangent to this curve because the curve's not continuous. Okay, so just sort of something to note there. It probably doesn't come up in anything you run into, but just kind of making a bit of an association between the limits we've recently discussed and the slope from before. Again, the term derivative, mean slope, and again, this is the equation that I was using on the other page. Limit as h approaches 0, and again, just using x instead of 8a's. And just sort of be forewarned, there are a number of other terms that have occurred in textbooks and in videos and around the internet talking about derivatives. And any of these terms or symbols could appear at some point, and they all just mean the same thing. So differentiating means finding the derivative. F prime of x is how we read this, and this is kind of the standard notation for derivatives. Leibniz and Newton, I'm going to say, although I don't remember for sure, we're both working on calculus simultaneously, so this is another, just dy dx is another notation that is often used for derivatives. Y prime, again, if f at x is the same as y, then y prime is the same as f prime. And this is just kind of a combination, d f at x dy. Excuse me. And I don't think you'll ever see these, but it's not impossible. We will focus on this. This is possible, and eventually dy dx actually becomes a little bit nicer for some of the stuff you'll see. I think it's not until next year, so we probably will see f prime at x almost exclusively. Occasionally I may write y prime just because I do that sort of thing. Those are the ones that, but just sort of know that there are a bunch of other things out there, and if you run into them, it is the same thing. So all that to say, something kind of interesting starts to happen when we start looking at our derivatives. Most of the questions we've done were fairly tough relative to the ones you see here, but these nice easy ones will allow me to sort of start to see some patterns. So given f of x being x squared, find f prime of x using first principles, sub in the x plus h, the x, and when I get down to about this point here, again, as always, my h's will divide out. I will substitute the 0 in for the existing h, and what I find is that f prime is equal to 2x. Now, before we sort of look at that too deeply, let's finish up this one. X cubed now, I have x plus h cubed minus x cubed. I've expanded that out. If you needed to, you could do it off to the side, but you won't have to do it. This is the expansion of x cubed, as was the case last time, and as is always the case. All my non-h terms up here subtracted out, so x cubed minus x cubed, and I'm factoring out an h, which then divides out the h in the denominator. And then I can also sub in my zeros. I have a 0 here, and I have a 0 here, which means that my f prime value, now that I've put the h in, the limit is out of there, is simply 3x squared. Because I have 3x times 0 and plus 0 over here. So if we look at our original questions now, I had x squared, my derivative is 2x. I had x cubed, my derivative is 3x squared. So it starts to look like there's a bit of a pattern here. The value out in front, the constant out in front, is my exponent. And as I've gone to the derivative, my exponent went from 2 here to 1, 3 here to 2. So it seems like there's a bit of a pattern. If we go back to the ones we looked at earlier now, see if this pattern kind of continues for us. Just pull these up a bit so I left myself enough room, plenty of room obviously. If I rewrite this question, one option is whenever we have a value in the denominator, we can flip the base and make the exponent negative. Typically we go the other way. If I have x to the negative 1, I rewrite it as 1 over x. But really this and this are the same thing. Same thing is true here. This is negative, negative, and x to the negative 2. And so looking at what we just sort of noticed up top, the exponent that was on the f at x is now the constant out in front of the f prime. The exponent on the f prime is 1 lower than the exponent on the f at x. Well, f at x is negative 1 here. Sorry, f at x is x to the negative 1 here. The exponent in the original was negative 1, and now the constant out front is negative 1. The exponent here was negative 1. This one is 1 lower at negative 2. And of course, I assume you know I wouldn't be showing you this example if it didn't work. Same basic idea here. This is x to the 1/2. Excuse me again. This is g prime at x being 1/2 x to the negative 1/2. Okay, so a combination of the negative in this example and the idea that square root is an exponent of 1/2. And one more time, the exponent here was 1/2. The constant out front of the g prime is 1/2. The exponent here was 1/2. 1/2 minus 1 is negative 1/2. And so what we end up realizing is that, at least at this point, all the examples had the same basic pattern. And so, and again, don't have to worry about that. The basic differentiation rules then. So these are for pretty much polynomials and anything that has a single term, I guess is probably a better way to say it, because obviously some of the things we saw that are square roots are not polynomials. F prime of x, so given that f at x is x to some exponent, f prime at x will be the exponent out front and a exponent 1 lower in the new exponent as the new exponent. There are a few more little rules here that we should have. The constant rule simply tells me, and don't worry about the names of these rules. These all will be very, very apparent as we sort of use them a little bit. But basically, this is saying what is the slope of f at x equal to 3. So if we think about the fact that f at x equals 3 is just a y equals 3 is just a straight line. The slope is, well, I rise nothing and run across, so the slope is 0. So if you take the slope of, or if you take the derivative of any constant, you get the value 0. And then these other ones, I don't even think they're really rules, but they always show up, and I'm sure you'll run into them in some of the notes that some things I photocopy. If you can look at any expression as a value times another expression, the value up front can be ignored. Okay, so that's probably poorly worded, but if we look at the examples that we already looked at, and I give you something like 3x squared now, the derivative of that, this part we said is 2x. The 3 was there all along, and so our derivative of this will simply be 6x. The 2 And again, this is very bad math talk, but the 2 comes down to the front, multiplies by the 3 that's already there, and then the exponent decreases by 1. Okay, so that's all that the constant multiple rule says. That basically, I guess I should have left that in. Basically, that if there's a number there, simply multiply the value with the exponent that comes down. And then a couple of others, again, sum rule, difference rule. If you have 2 terms added together, take the derivative of each one separately. 2 terms separated by subtraction, take the derivative of the 2 terms. Now, how does this actually look? If I now assigned this question, if I were assigned this question, I would rewrite it as x to the negative 1. And again, the negative 1's quote unquote brought out to the front. The exponent is 1 has to be subtracted from the existing exponent. The negative 1 minus 1 is negative 2. And then probably the original negative 1 over x squared is the nicer of the 2 solutions here. We tend not to leave things with negative exponents, but knowing that we can use them helps us a lot in this question. I think you can see that doing this was nicer than using first principles. If you can't, then you're crazy. And I think some of you might be. So square root of x here, again, convert it to an exponent so that we have a numerical value that we can A, quote unquote, pull out front, and B, subtract 1 from, and then basically just return it to a more proper form with a non-negative exponent. And I have one more example written, so I might as well pull it up. So this is kind of taking into consideration a little bit of the various things the other rules we saw. So first thing is the 3 terms are added and subtracted. I will simply work with this first term on its own, the second term on its own, and the third term on its own. In this case, it's actually the example I guess I had up. No, it isn't. Sorry. The exponent is 3, comes down to the front, quote unquote. I can't see me doing quotes, but I keep doing quotes every time I talk that way. So 3 times the 2 is going to be 6 out front. Subtract 1 from the exponent is x squared. This has an exponent of 1/2. The 1/2 gets pulled out to the front, multiplied by the 6 will be a 3. And 1/2 minus 1 is negative 1/2. A constant, again, all constants, the first derivative will give us 0, or the derivative will give us 0. And so simplifying a little bit here, 6x squared, 3x to the negative 1/2, and again, positive exponent for the last term. Okay, so I'm going to stop there. It was a little bit longer than usual, but I thought I wasn't recording again. It scares me every time. But it is, you see sort of a fairly nice set of rules, and that's what we'll be working on for the next day or so, and then obviously moving forward with some more advanced rules as we go.